This is an introduction to Lab 1 for CPE 133. In Lab 1 we are going to be conducting two experiments. Experiment 0 to design the half adder and Experiment 1 to design the full adder. Now why are we starting with these adder circuits? Because adding is one of the most basic components, most basic elements of digital design. Virtually everything you do on a computer can boil down to simple arithmetic. So it's very important to understand how an adder is created and what goes into adding numbers in a computer. So the other purpose of this experiment, however, is to just get you to understand how to go from a digital design concept in your mind and on paper and get that into an actual development board or into an actual physical digital circuit. So you're going to be exposed to using all the tools, going through the design process, and just becoming familiar with all of that. And that in itself is going to take a bit of time and involve a learning curve because you'll be learning new tools, you're learning a new design language, VHDL, and so don't get frustrated as you're going through this process. It will become much easier as the quarter goes on. So just keep that in mind as you are doing this for the first time and don't get frustrated. Okay, so what is a half adder and a full adder? Well, hopefully if you had done your reading in chapters 5 through 7 this week, you would have read about it. But in case you haven't, I would highly recommend going back to the text and reading about the half adder and the full adder. But I'll just give you a little bit of a primer here. So let me pull up Excel. Alright, let's say we want to add the numbers 11 and 7. So there's our number 11, here's number 7. Okay, so back to elementary school, you write up your ones place, your tens place, and your ones place, and okay, you line them up nicely, and you start adding. 1 plus 7 is an 8, and 1 plus 0 is a 1, there's no carry. Okay, I got 18. Alright, so we can do the same thing in binary. So what's 11 in binary? Well, it's 1, 0, 1, 0, 1, 1. Remember, that's going to be a 1 plus a 2 plus an 8, so we got 11. And we're going to add that to 7, which is going to be a 0, 1, 1, 1. And let's go ahead and add those together. Let me remove this bar here, no border. Alright, so the same thing. Like we added in decimal, we're going to go ahead and add in binary. We start by having two inputs, 1 plus 1. What is 1 plus 1 in binary? Well, 1 plus 1 in binary is 2, but we can't represent it with the number 2, so we have to represent it with a 1, 0. How are we going to do that? We're going to say it's 0, carry the 1, because guess what? This is the 2's place, so we can carry that 1 over. So now we have 1 plus 1 plus 1. What is 1 plus 1 plus 1? Well, it's 3. Can we represent a 3? Well, no, but in binary, a 3 is a 1, 1. So here we can do, it's going to be a 1, carry the 1. Alright, so now we have a 1 plus 0 plus 1. That's going to be 2, which is going to be 0, carry the 1. Again, we have a 1 plus 1 plus 0, which is going to be a 2, which is 0, carry the 1. And so our final result is going to be a 1, which is our carry that resulted, and our final sum is 0, 0, 1, 0. So what is 16 plus 2? Guess what? That's 18! Amazing! Okay, so what's a half adder and a full adder? Well, can you see a difference going on here? Aha! The half adder is this first adder right here. Notice the very first adder that we have only takes 2 inputs. There's no carry to begin with. It's just the 2 least significant bits of the operand. So this is our half adder. And then look, every time after that, we have a full adder. So this is a half adder, and this is a full adder. The half adder has 2 inputs. The full adder has 3 inputs. Okay, so now that we know what a half adder and full adder is, we need to come up with a truth table to describe the relationship between the inputs and outputs. And what are the inputs? Well, we have the half adder has a 2-bit input. We can call our operands A and B. and it has an output which is a sum and an output which is a carry. So we can go through putting our inputs and our outputs, carry and sum, all possible combinations of our inputs. And now we know 0 plus 0 will give us no carry, no sum. 0 plus 1 will give us no carry, 1 sum. 1 plus 0 will give us no carry, 1 sum. And 1 plus 1 will give us a 2, which is a carry sum, a 1, 0. Okay, so now we've described the relationship between the inputs and the outputs in the truth table. We can now create an equation in whichever form we'd like. So we can say carry is going to equal, I'm going to use SOP form, AB, and sum is going to equal A naught B, or A B naught. And there we go. Now we're ready to enter these equations into our VHDL module and implement this half adder on our board. So you can do the same thing with the full adder. With the full adder, though, you're going to have 3 inputs, A, B, and C, and 2 outputs, carry out and sum. And then with 3 inputs, how many possible input combinations are you going to have? Hopefully you said 8, so you can fill in all those 8 possible combinations, and then fill out what your carry and sum should be for the full adder given the operation that you want to have happen. Okay, so that is what a half adder and full adder is. So let's talk about what you're going to be doing in this experiment. So I want to draw your attention to Polylearn, which first has this video link for Intro to Project Navigator. And the Intro to Project Navigator goes through the whole Xilinx design methodology process. That is, how do you go from a concept in your head, in this case an adder, to actually implementing it on an FPGA. And so this goes through the whole design process based on the example of the bacon ice cream chocolate syrup that I've been giving you in the previous videos this week. So this tells you how to implement that circuit on the board. So watch the video, follow along, and that will give you a whole introduction to the tools and the design process that you will need to follow for Lab 1. Okay, so let's look at Lab 1. So what you're going to be doing is you're going to be creating this half adder. You're going to be mapping the inputs and outputs according to this table to match the inputs and outputs on your board. So you're going to use the switches for your inputs and the LEDs for your outputs. You're also going to be using iSim, which is talked about in the Intro to Using the Tools video. This is going to allow you to simulate your design in a software environment. And then you're going to go ahead and test your design on your board and answer these questions in your lab report. And then you're also going to create the full adder. So the first thing you want to do is create a design or a project with the half adder, and then finish that up and create a whole new project with the full adder and follow this assignment. In both assignments, you're going to be following the exact design methodology shown to you in this video. So again, watch this video first and follow along with it so you get to know the design methodology, and then you're going to be doing it twice, once for the full adder and once for the half adder. So once you and your lab partner have completed both experiments, what are you going to do? Well, you're going to write up a lab report and you're going to turn in a lab demo video. So on Polylearn, I have posted the lab activity report guidelines, which go over what I'm looking for in the lab. So first off, it gives some general rules about the lab report. Now each and every person needs to turn in a lab report. That means by Sunday at midnight, each person needs to upload a report to Polylearn. Now, you and your lab partner can write the same exact report. So even though you're uploading the same document, each of you have to upload it. So you can write the whole report together. The only thing that needs to be written individually is the conclusion, because the conclusion is your own personal reflection of what you learned and gained from doing this lab. So once again, each and every single person needs to upload a lab report, but you can write all of the report except for the conclusion with your lab partner. Okay, so those are some general rules. Be sure you go over all these bullet points to see what I'm looking for. Now, the report format has 5 major sections. It has the objectives, which state why you're bothering to do the lab. Your procedure, which says what you did. And in the procedure, you're going to go through the step-by-step procedure, providing a black box diagram, maybe a truth table, maybe a circuit diagram, whatever you needed that was useful for creating this particular digital design. Then you'll have a testing section, and your testing section will often include a screenshot from iSim with you then explaining your screenshot within the text, saying why you think that the screenshot is showing me that it's working correctly. And it will also include a table showing your different test cases, your expected outputs for those test cases, and then what you actually got. So you can verify visually that you got what you expected, or if you didn't, explain why that's the case. Then you'll have a section that answers the questions. So at the end of each experiment, there are questions that I'd like you to answer that sort of try to get to a little more deeper understanding about what you're doing in the lab. And then you have the conclusion, which is summing up the experience, and then I have a whole discussion about the conclusion below. And then the last thing will be your appendix, which is your VHDL code. So then I go through describing what a conclusion should contain and not contain, and what I'm looking for in the code that's attached. So please go through and read this document and let me know if you have any questions. Also, I have posted on Polylearn an example lab report. Now, this doesn't have the cover page because I didn't want to include other people's names, but it sort of gives you sort of a flow of what I'm looking for. In red are my comments, and in black is what a previous student had done. This is for an experiment that we will not be doing in this course. So you see, we start with the objective, then we have the procedure, and it's important to have all your figures with figure labels and captions, and then have them referred to in the text. So don't just put a figure in, be sure to have text that describes it and also points to that figure, so that way when you're reading through this, you could be like, okay, I'm reading about this, and it's, oh, I gotta go look at this figure, okay, that's great. So again, all figures and tables need to have captions and labels and be referred to within the text. So this kind of goes through the whole procedure, and then there's the testing section. In this case, they didn't do an iSim screenshot, but you should be doing that in most of your reports unless otherwise stated. But here there's a nice table showing the expected outputs and what they got, and explaining what was going on in this table. Then they have answers to the questions, and then they have their conclusions. And here I have put some examples of what I think is a decent conclusion. It's sort of talking more about why rather than what. So don't just, again, summarize what you did in the lab. Tell me why you did it, how it relates to your general understanding of things. So take a look at these and see sort of what I'm looking for in the conclusion. And I did not include code in this report, but this would then be followed by your code. So you're going to be turning in one report. Each person is turning in one report with an individual conclusion, and the one report is going to cover both Experiment 0 and Experiment 1. So it's going to use, you're going to write one lab report that covers both of these experiments. So you could talk about first creating the half adder and then creating the full adder, and be sure you answer questions for both. Now, you'll also need to do a demo. So here I have a demo guideline. So in your demo, again, each person is going to have to submit a demo. So you and your lab partner each need to submit a demo. If for some reason you can be together and create one demo between the two of you, you can each upload the same file. But you can do it individually and each upload a video. So you must state your name and show your face in the demo video. Your video should be less than 1 minute. You should clearly state what your design does and what all your inputs and outputs are. So don't just be flipping switches and thinking that I know what's going on. You should be clearly explaining what you're doing and clearly showing me the test cases you are trying. That should make me feel that your design is working correctly. So you will be creating for Lab 1 just a demo for Experiment 1. I don't need a demo for both the half adder and the full adder. I just need a demo for the full adder. So again, to recap, what we're doing for Lab 1 is you're implementing Experiment 0 and Experiment 1, so you're designing the half adder and the full adder. You and your lab partner will write one lab report for the two experiments, and each individually submit it and write your own conclusion. And you will be each submitting a demo video of your Experiment 1 of the full adder onto Polylearn. And on Polylearn, you'll be uploading your report to the Lab 1 report upload, and you will be uploading a link to your video onto the Lab 1 demo upload forum. So just create a new post on the forum with a link to your video, whether you put it on YouTube or Dropbox or wherever you want to be putting your videos. Just put a link there so that I can easily view it. Thanks.